Welcome back. Now let's take a look at how Boltzmann came up with a general approach to count the number of microstates in a given macrostate. Now before we get too far, it's a good idea to go back and review the last section of Chapter 1. In that section, we learn how you could get the equations of motion from the kinetic and potential energy functions. In that section, we learned about the Lagrangian approach, and then after the Lagrangian approach came the Hamiltonian approach. And it's the Hamiltonian approach that we will use in this chapter. Now, in that approach, Hamilton proposes a total energy function, which is simply the sum of the kinetic and the potential energy term, and that total energy function is now called the Hamiltonian of the system. And from that Hamiltonian function, you can derive 6n first-order coupled differential equations to describe the time evolution of the system. So for n particles, there's going to be 6n coupled equations of motions describing the rate of change of the positions and the momenta in the system. Now, those coordinates, the 3n position coordinates and the 3n momentum coordinates, can be put together to create a 6n dimensional space. So you can imagine, one-dimensional space, two-dimensional space. Now try to imagine a 6n dimensional space, and in that space, which is what we call phase space, the system state at any instant in time, which is when it's in a given microstate, is going to be represented as a single point in that phase space. So a single point in that phase space represents the microstate, a system that's in a given microstate. Now, as the system evolves in time, that point in phase space will move along some trajectory. And now, if the Hamiltonian is time independent, which it is in our case, then the system state will move among microstates on a hypersurface of constant total energy in this phase space. Now, I know that's a lot to kind of digest, so to kind of go back and think carefully about this, but this is the sort of underlying theory that Boltzmann builds his approach for counting microstates. So we see the microstate as just a single point in this phase space that's then, as the system evolves in time, undergoes some trajectory along some hypersurface. Okay? Now, the approach of Boltzmann, which is similar to what we did in the previous video, is to discretize phase space. So in the previous video, we discretized the volume that the sample is in. Now we're going to discretize phase space. And so in this approach then, at any instant, the macrostate, the system, will be in one of these discrete microstates that we've obtained by discretizing phase space. Okay. So in this approach, we're going to have to pick sort of a discretization size. So if you can imagine, like on your TV screen, you have your pixel size. So if you have a 720p or 1080p or 4K TV, you have progressively smaller and smaller pixel sizes. So in phase space, this 6n dimensional phase space, we have our sort of pixel width, right? Our voxel width that we had in the previous lecture. So we can see that we're going to pick a delta Q and a delta P for our width for each of those coordinates. So those 3n coordinates. So there'll be 3n delta Qs and 3n delta Ps. And for each set then, we're going to define, well, this is what Boltzmann does. He defines the product of delta Q delta P for a given coordinate pair as equal to some constant. And this constant sort of defines the degree of which we discretize phase space. Now, this constant has the same dimensionality, by the way, as angular momentum. Now, what Boltzmann didn't know about in 1877 when we proposed this approach is that in 50 years later, Heisenberg would propose the uncertainty principle in 1927, which tells you that there's a lower limit on what this product can be. Actually, this product can only be as low as Planck's constant. So we'll learn more about the reason for that later in the course. But for now, we'll take the fact that this has a lower limit and set our discretization constant h here as equal to Planck's constant. So in our 6 n-dimensional phase space, then, we have these hypervolumes, these small cells that have a hypervolume that is given by this volume here. So it's h to the 3n is the hypervolume of each of these discretized cells in phase space. All right, so now what we want to do is to learn how to count microstates associated with a given macrostate. But we're going to start with the simple examples first and then work our way up to a more sort of realistic problem. Now, the easiest case would be a single particle moving in one dimension. So let's just take that to kind of get some of these concepts clear. So for a single particle moving in one dimension, we would have just one position coordinate and one momentum coordinate. So the Hamiltonian would look like this, where this is the kinetic energy term and we have some potential energy function. In this case, we're going to take a simple potential energy function where the potential energy is 0 if the particle is between minus L over 2 and L over 2, and it's infinite otherwise. So in other words, we've created a potential energy function that traps the particle between the two limits minus L over 2 and L over 2. So with this potential energy function and this Hamiltonian, we know that if the particle has a fixed energy, E, then it can only have momenta of plus or minus the square root of 2me, okay? And it can have any value of q between plus or minus L over 2. So if we create a phase space for this simple case, a single particle moving in one dimension, which has the coordinates momentum and position, then that's a two-dimensional space, phase space. So that's easy for us to visualize. And in that two-dimensional space, which I plotted here, here's the momentum, here is the position here, and we've discretized it with our discretization here, and you can see here's all of our phase space cells. Each one of these cells corresponds to a particular microstate that the system can be in, but now the ones that are consistent with the total energy, I've colored in green here. So here are all the states that are consistent with the microstates with the total energy. So now if I want to count microstates that are consistent with the total energy, then I would just go through here and I could count all of those. And that would be the number of microstates associated with that energy, okay, in this particular problem. Now, if I wanted to sort of, set up this counting with an equation, I could do it this way, where I can have a double summation where I sum over every possible coordinate cell in the position and every coordinate and momentum, and that double sum then is then a sum of this function called the Kronecker delta function, which simply compares the total energy to the Hamiltonian evaluated for each one of these cells. And if the Hamiltonian is equal to the energy, then it returns 1. If it's not equal, then it returns 0. So for each one of these cells, the summation is the sum over every single cell, and it asks the question, if I evaluate the Hamiltonian for this value of momentum and this value of position, I get an energy. Is it equal to this E? If it is, then I set it equal, I return 1. If it isn't, then I return 0. And this way, when this sum is complete, this will have effectively counted all of the green cells here and not counted all of the ones that aren't shaded in. All right? So that's the approach here. That's how we're going to count microstates in this simple case. And this is the equation that we use with this function that I call the Kronecker delta function. All right? All right, so that's one particle in one dimension. Let's go slowly. Let's go to one particle in 2 dimensions. And how does that make the problem, more complicated? Well, next thing we see is, we have to add then the kinetic energy has 2 terms here because now there's two dimensions, means we have a momentum along 2 different directions, and we have the position, Q1 and Q2, and we're going to define similarly a potential energy function that traps our particle in a box, a 2-dimensional box that goes from minus L1 over 2 to L1 over 2, and then from minus L2 over 2 to L2 over 2, and that's our function here, and it's infinity outside. So in this one particle in 2 dimensions, we have a 4-dimensional hyperspace. Now already, this 4-dimensional phase space, now already I can't plot that on, particularly on a 2-dimensional screen here. So we have to sort of start thinking and imagining this. But this is a 4-dimensional space. And if we think about the system, which has a fixed energy, then that constrains the allowed microstates to be on some hypersurface in this 4-dimensional space. In fact, actually, that hypersurface is a hypercylinder in that 4-dimensional space. And I would do the counting just like I did before. I would do a summation over every Q1, Q2, P1, P2 in that grid of discretized cells, comparing H to the fixed energy, and again giving me either 1 or 0, and that would count all the cells that we have. But again, it's hard to visualize this 4-dimensional hyperspace in this hypercylinder. So if I take, say, a cross-section out of this 4-dimensional hyperspace, cross-section taken at 2 position coordinates, Q1 and Q2, then I would have a plot of P1 versus P2. It's just so you can see that these are what the allowed microstates would be in that cross-section. And what you see is that it's a circle. So the Hamiltonian here really is just describing a circle, which is the surface of this hypercylinder in this 4-dimensional space. And so what we're doing is we're counting every one of these microstates on the surface of this hypercylinder, and of course then it extends out with other positions along Q1 and then also along Q2, if you can imagine, in 4 dimensions. All right. Okay, so now we've done one particle in 1 dimension, one particle in 2 dimensions. We've moved from a 2-dimensional phase space to a 4-dimensional phase space. So now we need to make the jump, and we need to imagine we have n particles, and n can be an Avogadro's number, 10 to the 23rd particles, and we want to construct a phase space of that. All right, and this is where we come to what's called the microcanonical ensemble in statistical thermodynamics. So now we're going to imagine we have n particles in a 3-dimensional box, and it's got some total energy. And so the example would be like, just imagine you have some monatomic gas that's an isolated system, so it's single phase, single component, and we know the total energy of that system, and we know the Hamiltonian for that system, and that means in that 6n dimensional phase space, there's going to be a hypersurface that is defined by the total energy. Right. And what we call the microcanonical ensemble is all the microstates that lie on that hypersurface that's consistent with the total energy. And again, we're going to count them, and now I'm going to do a summation. I'm going to sum over all of the cells in this 6n dimensional hyperspace. So my summation is going to go from a sum for Q1 all the way out to Q3n, and then P1 all the way out to P3n, and for that entire sum, then I'm going to evaluate the same kind of Kronecker delta function where I looked at each cell and I compare the Hamiltonian value for that cell with the total energy, and if they're equal, then I return 1. If they're not equal, I return 0. And this way, I get then in this sum the total number of states that are consistent with the total energy, the total number of microstates. All right. Now, in this summation, I also have to divide by this factor here to account for the indistinguishability of particles. Now, if you remember in the previous video, we talked about how we can't distinguish whether particle 1 is in this cell and particle 2 is in this cell, or vice versa, because they're indistinguishable. And again, that comes from quantum mechanics, and we'll learn more about why that happens. But for now, we're just going to take that as something we have to account for at this point in the treatment here. So what we're going to do is, just like we did in the previous lecture, we will divide by 1 over n factorial if we have indistinguishable non-localized particles. Now, if we were in, say, a solid phase where the particles were all fixed in space and they were localized, then we wouldn't need to do that. And so I will just set that equal to 1. All right. And similarly, like the previous lecture, we also assume that the discretized volume cell is either empty or at most occupied by a single particle, in this case here, all right, in this classical treatment. All right. Now we can make the classical limit approximation when the system energy is high enough, that is to say at high temperatures, that the hypersurface appears continuous in our pixelated or voxelated phase space. Okay, so we know that in those earlier pictures that I showed you, that the sort of surface of our hypersurface was not continuous. We could see the discreteness of our phase space. But at high enough energies, when we go further and further out, as our energy increases, this sort of hyper cylinder gets bigger and bigger diameter, then that gives us a more continuous looking surface. Just like when you imagine when you go to a higher resolution screen, it's harder for you to see the discretization. So in the limit that you have a high energy, this summations can be replaced with integrals. And in that case, our counting integral or summation becomes an integral. And you can see now we have this expression where we've replaced all of these summations with integrals, and we've replaced the function here with a function that's now called the Dirac delta function, which is a function which is either infinity if the argument is 0 or 0 if the argument is non-zero, and that's something we learned about in chapter 2. But the important thing about that function is that the integral over all values is 1. So in other words, it's even though it goes to infinity, it's infinitely narrow. So that integrates to 1 over all values, and that allows us to select out, essentially count which energies are on the hypersurface that matches the Hamiltonian. So then the only other difference here between this and the previous expression is that now we have to divide by this hypervoxel volume, because now this is a volume integral and we want to turn it into a count, and so we have to divide by the volume of this hypervoxel. But otherwise, that's all you have to do when you want to go from the discrete picture where you have quantized phase space to a continuous version of that. But mostly we're going to stick with the discretized phase space because that's actually the true quantum nature of phase space. Okay, now let's take a look at counting. What I'm going to do is I'm going to take this really massively large number of summation symbols. You can see this is n is 10 to the 23, so this is 3 times 10, n to the 10 to the 23 summations here and here. And let's see if we can reduce that down a bit, at least for the math point of view. And what I'm going to do is I'm going to write down that in my phase space, I'm going to take every cell and I'm just going to assign in phase space an index. I'm going to call that index gamma. I'm going to call it gamma infinity in this case because I'm going to count all of the phase space cells. So there's an infinite number of phase space cells. And I'm going to say that I'm going to go through every cell in phase space, and I'm just going to ask the question, is H equal to E? And then if it is, then give me 1. If not, give me 0. And that is going to count the number of microstates as consistent with the total energy in the phase space. Now this is an infinite sum, but then once I know this number, then I can do a sum over only those cells which are consistent with the total energy. And then once I know those cells, then I can calculate the equilibrium properties of any thermodynamic property of the system. So in other words, if I wanted to calculate some ensemble average over all these possible cells, I can just take then a summation, and now my summation is only over the cells on the hypersurface that's consistent with the total energy, and I take then that summation, and gamma runs over the accessible microstates. The y is some property which is evaluated for each one of those microstates. P is the probability of being in one of those microstates, and then when we do that summation, we get the average property for the system if it had visited every one of those microstates on the hypersurface that's consistent with the total energy. And so for the probability of each of these, we just assume that every one of those microstates that's consistent with the total energy is equally probable in this sum. All right? So that's the approach for calculating an ensemble average, all the microstates that are consistent with the total energy, the accessible microstates. Now, the question is, in reality, the macroscopic equilibrium property is actually what you see in a time average. Over time, the system is evolving through all of these different states, and if you observe it between some time period, and in the limit that time period goes to infinity, you get some average property. And the question then is this time average equal to this ensemble average? And that's a big question in statistical thermodynamics. That's still people struggle with. And so the question is, does this ensemble average give the same result as the time average? And this really took a lot of time for Boltzmann to try to justify, and I'm not sure if he actually justified it to most people's satisfaction, but he came up with this justification with the idea of what's called an ergodic hypothesis, or saying that it was an ergodic system, that the system moved in phase space on this hypersurface over time, and it visited every single hypercell or microstate on that surface, and that was the justification for saying that this ensemble average was equal to this time average here. Now, there are arguments against the ergodic hypothesis, and it was pointed out to him by many mathematicians at the time, so it really was a problem that Boltzmann struggled to try to prove. But now it's kind of just understood that this is going to be a postulate of statistical thermodynamics, because it just turns out that if you apply this approach, you get the right answer. And this was the approach that Gibbs took in his formulation of statistical thermodynamics, that just assume that this probability distribution, that this is the probability that you use, is going to give you the right answer, and in fact, actually, it does. So it's just accepted as a postulate of statistical thermodynamics, sort of justifying that why this is true is kind of beyond the scope of this class, and you may need to talk to sort of other scientists in statistical mechanics to have long discussions about that. All right, so that's it for this video. In the next, we'll look at other types of ensembles and constraints on the system.